So good evening everyone. Are you all able to hear me?
Yes, ma'am. Good evening.
Yes, ma'am.
Okay. So this session is going to be just like the previous session. So first we will have a recall session. Whatever we have done in the previous session, we will have a quick recall, and then we will cover the topic determinants today. So determinant, you have two sessions this week. So those two sessions we will be covering today, and we will be solving some problems as well. So after we finished all this, if you have any queries, you can ask at the end. Is that all right? Okay, and in between, if you have any doubts also, you can ask me. Okay.
Yes, ma'am.
Okay, fine. So let us quickly recall whatever we have seen in the previous class. So in the previous class, first we started with vectors, right? So you saw vectors in which space? Do you remember? In Rn, right? Particularly you saw from R2 and R3, right? So what is R2 and R3? Those things do you remember? So for example, if you have a vector x1, x2, it is in R2. If you have another vector, it is in R3, where these elements x1, x2, x3 are from real number. All right. So now this is a vector from R3. So you can add two vectors from the same space, right? And you know how to add. So if you are having two vectors, okay, so the addition will somewhere lie like this. So this you have seen. And what is mean by scalar multiplication? So scalar means we are mainly talking about here a real number. We are multiplying a vector with a scalar that is a real number. So usually we denote scalars with some constants like alpha, beta or k, c and all. So alpha times of a vector x, let's say, it means what? So this is, let's say, x. Then what is alpha x? Alpha x1.
Alpha x1, alpha x2, alpha x3.
Right? So in R2, what happens when you do scalar multiplication? Suppose you have a vector like this, and you are doing a scalar multiplication. If this alpha is a positive value, then what happens? This vector is just extended. Okay, I'll draw it correctly. So this vector will just get extended when your alpha is positive. For example, if you take x is equal to, let us say 1, 1. So you know where is 1, 1. So 1, 1 is this point. So this is your vector 1, 1. Now what happens when you multiply this x equal to 1, 1 with, let's say, 2. So 2 times of 1, 1 is equal to 2, 2. And this lies here. So what happens to this scalar multiplication? This vector just gets extended like this. And what happens when your alpha is negative? Let's say you are having maybe minus 1. Alpha is minus 1, let's say. If alpha is minus 1, then what happens? Can you tell?
Yeah, it is in opposite direction.
Yeah. So if alpha is minus 1, so your alpha x becomes minus 1, minus 1. So still it lies along the same line, but now it goes in the opposite direction, right? So maybe, let's say this is the point minus 1, minus 1. So it gets extended in this direction. Okay. So anyway, scalar multiplication, what it does? It just extends the vector either in this direction or the other direction. Alright, so scalar multiplication does not change the direction of the vector. But what happens in the case of vector addition? The direction is changed. Now I'll ask you a small question. Is it always that if you add two vectors, the direction gets changed? Do you understand my question? Let's say you have two vectors x and y from R2. X is a vector from R2 and y is a vector from R2. So is it always that x plus y is in a different direction than x and y?
No, ma'am. It is not necessary that.
Yeah. For example, if x and y are both, for example, if you have some vectors like this, let's say 1 comma 0 and y is, let's say, minus 2 comma 0, then what happens to x plus y? X,
minus 1 comma 0.
it still lies along the same x-axis. All of them lies along the x-axis, right? Okay. So this is the general outline about vector addition and scalar multiplication. Okay. So next, what is the next topic we have seen? We saw what are matrices. What is the main thing about matrices? Matrix consists of, it is a rectangular array consisting of rows and columns, right? So what is the size of a matrix in terms of rows and columns? So if you have m rows and n columns, what is the size of a matrix?
M cross N.
n cross n.
M into N.
Yeah, so m cross n is the size of the matrix. And what are the matrix operations you have seen? Addition, scalar multiplication, multiplication and transpose. Addition is very simple. What do you do? Suppose you have a matrix A. Do you know this representation? Yes, right?
Yes, ma'am.
So what is this representation? The elements of A are represented as ij, where I and j are varying from m to n. So your I varies along m and your j varies along n, right? So if you have to add two matrices, both of them first of all should be of the same size, right? So when you have the same size, then what can you say about A plus B of ij? You know it is Aij plus Bij. So you add entry wise for matrices. And what about scalar multiplication? So again scalar, you know. So let's take a scalar alpha and you multiply with A. How can you write the ijth entry of alpha A? It is alpha times, yeah?
Alpha Aij.
Yeah, alpha Aij. This is your ijth entry of the scalar multiplied matrix. Okay. And matrix multiplication is a little more complicated than this one, but I guess you are now familiar with matrix multiplication as well. So for two matrices, I guess you already know. Suppose you have two matrices like this. Let's say, what do you do? First, for the first entry, you kind of do a dot product of the first row with the first column and fill it here. And similarly, first row with the second column, you fill it here. And so on. Right? This is matrix multiplication. And
Ma'am, one thing, can you please explain one's cross product? I forgot that. Is it possible?
so the dot product is very simple. Suppose let's say
Cross product.
Cross product is not required here. So we will see it when it is required. Okay, here you are doing only the dot product.
Okay.
Alright. Okay, fine. So yeah, now we are the next thing is we are going to look at transpose. Again, this is a very simple one. Suppose you have a matrix. I will write some simple matrix. Can you say what is A transpose?
Row में
Just
column.
the row and column with each other.
314
तेव्हा A matrix
3
मध्ये
minus
314 असतो row
314
minus 5
minus
5
0
535
minus 37.
0 minus 37.
Yeah, very good. So you know how to do transpose of a matrix. All right. Okay. So these are the basic matrix operations. And then what are the matrix types? In general, any matrix is a rectangular matrix. So there is nothing specific about rectangular matrix. All matrix you can call rectangular. But what is a square matrix?
If
Number
row
of
and
rows
column
equal
both
to
are
number
same.
of columns.
row
Yeah.
and column.
If you have m is equal to n, then it is called a square matrix. Right? Okay. What is a diagonal matrix?
Non-diagonal entries are 0.
Yeah. So how do you represent diagonal entries? Suppose you have A equal to Aij. Which entries are called the diagonal entries?
AI.
Yeah. So Aii or the diagonal entries. Right. So if you have, so for example, you have 1, 2, 3 and all other entries are 0. This is a diagonal matrix. Okay. What is the next type you are having here? What is a scalar matrix?
All the diagonal entries
All
are
diagonal
same.
entries must be
All the
same.
diagonal entries are the same. So every scalar matrix is a
Diagonal
Diagonal matrix.
Diagonal
is the
matrix.
converse true? Converse is the
No,
same.
ma'am. No, no.
Yeah. So for example, we have this itself. So this is a diagonal matrix, but is this scalar?
No,
No,
this is not
no.
scalar.
Yeah. So this is not scalar. Okay. What is a zero or null matrix?
All the elements are
All
zero.
All
entries are
elements are zero.
Yeah. All the elements are zero. So this is an example of a zero or null matrix. And what is an identity matrix?
diagonal.
Diagonal
All
elements
some elements are one.
All
Yeah.
there are
So,
zero.
can you say what is a diagonal? Sorry, identity matrix. Is it any one of this type?
No,
No, ma'am.
Not any of the previous type?
no.
Sure.
It is a scalar
It is a
matrix.
scalar matrix with the diagonal values as 1.
Yeah, you can say it as a scalar as well as a diagonal matrix, right? Because all the non-diagonal entries are zero, and also all the diagonal entries are same. So in particular, it is also a scalar matrix, right? Okay, is this clear?
Yes, ma'am.
Yes, ma'am.
Okay. What
Ma'am, I
about
have
the, yeah,
I have a question in
yeah,
matrix.
yeah.
Ma'am, I wanted to ask about this submatrix.
Okay.
So, ma'am, submatrices are the matrices like we can find, like if I have a matrix A,
Mm,
and then we find out the submatrix by
mm,
removing any numbers of rows or
mm,
columns, correct?
mm. Yeah.
So, ma'am, I wanted to ask two
Mm,
questions related to this. So, ma'am,
okay.
if I remove all the rows and columns and then it will become a 0, 0, let's say, then will that be a
Just a
submatrix?
minute. Just a minute. If you are removing all the elements, there is no matrix at all.
Also,
I
that
guess
so 0, 0 cannot be a submatrix. I mean, zero matrix cannot be a submatrix, right?
unless it is a null matrix or there is a zero entry in that in the
Okay.
matrix.
So, okay. So that means it's not possible for a non-zero matrix, right? And
Mm.
then another thing is I wanted to ask,
Mm.
is this the same like submatrix and subset both have the same concept or subsets are different, like subset of a matrix?
Subset. There is no concept of subset of a matrix. If you have a matrix group of matrices, let's say, then there is a subset. For
Okay.
example, if you consider all the diagonal matrices as
Mm-hmm.
a set, then
Okay.
the set of all scalar matrices form a subset of the diagonal matrices.
Oh, all right. So like there is nothing like it's not same, right?
Yeah, if
Okay.
you consider one single matrix, then there is no concept of subset. Only you have a submatrix.
Okay, ma'am. Okay. Yeah, got it.
Okay?
Thank you. Yeah.
Okay. And what are triangular matrices? What are triangular matrices? So let us say you have,
When
yeah,
the elements above the
Upper and lower
diagonal elements
triangle.
are 0 or below the
Elements
diagonal elements
Above
are
above
0.
or
or
below
below
diagonal
the
element.
diagonal is 0.
okay. So A31, A32, A33. Let us say you are having a 3 by 3 matrix like this. Can you explain triangular matrix? First, let's say upper triangular by putting some conditions on Aij.
Then A20, A21, A31, A32 has to be
I
0.
greater than j should
I
be 0.
less
It
than
is
j
0
is 0.
if, what is the
Okay, I
relationship
yes.
between A
I
and J?
I less.
I greater than 0.
I
I
greater
greater than
than
0.
G.
I is
I
greater
greater than
than
j.
J. This is for upper. And how can you say the same for lower? Aij is 0 if
I is smaller
I
than
should
j.
be less than 0.
I is
less
less than
than
j.
J. Okay, you see I is less than J. So this is how you can define upper and lower triangular matrix. And of course, you know. So in the 2 by 2 case, for example, so this is a example of,
Upper triangle.
yeah, upper triangular matrix. And this one is an example of
Lower.
Lower
Lower
triangular.
triangular.
lower triangular matrix. All right. Okay. So next we have seen what are the different matrix types. Okay. So next we saw what is a system of linear equation. Okay, so a system of linear equation means, for example, if, let's take a very simple system. If you have 2x plus y is equal to 1 and 3x plus 2y is equal to minus 2. So now this is a system of linear equations. Linear in the sense that the powers of x and y are just 1. Okay, so this is a, yeah. So this is a linear equation. Now, how many equations are we having here? How many equations we are having? We are having 2 equations. And how many unknown variables are there?
2.
2 equations and 2 unknown variables. Okay. So now in general, this is a specific example where you have only 2 equations and 2 unknowns. Now here you have a set of linear equations. Can you say how many equations you are having here in this set?
N.
And
N number of equations.
How many equations?
M
It is
equation.
m equations.
yeah.
Right? See, 1 to up to m. So you have m equations. And how many unknown variables are there?
N.
Okay. So n unknown variables. Okay. So now how to represent it as a matrix? I guess you all know. You just pick all the coefficients of this x1, x2, xn from all the equations and put them in the matrix form. And what is the name of this matrix?
Coefficient
Coefficient
Yes, you are simply collecting all the coefficients. So this is called a coefficient matrix. Okay, this is a coefficient matrix. And this x is your unknown variable or unknown vector.
Column vector.
Yeah. So this is your unknown vector and this is your constant vector. Okay. So this is how we write a system of linear equation into the matrix form. And what are the possible solutions for any system of linear equation? You can
Three
have
solutions.
3 cases. What are the cases?
Unique
No solution, many solution,
or infinite solution.
unique solution.
Yeah. Yeah. So in 2D, it is very easy to see it through graphs. So here you are having 3 graphs. Can you say which one represent which type of solution? So here
First one has no solution.
No
The
solution.
second one has unique
Unique
solution.
solution.
And third one has many
Infinitely many
solution.
solutions.
Unique
And third
solution.
has infinitely many solutions.
Infinitely many.
yeah, infinitely many solutions. So here you see that these 2 lines are not intersecting, so there is no solution. Okay, so these 2 are intersecting and this point is a unique solution. And here you are seeing only one line. So where is the other equation? Where is the other equation?
Overlapping.
On the same line.
Overlapping.
That's coincided on the same line.
Exactly. So what are the common solution points in this graph?
Infinite.
No, what are the, for example, this point is your unique solution here. So here in this graph,
Here
Whole line.
all points on the line.
so all points on this line, all points on this line will give you the solutions, right? All these points together is a set of infinitely many solutions. Okay, fine. So you know these types of solutions. Now shall we move to the topic of determinants?
Ma'am, in
Yeah.
triangular matrix,
Yeah.
if means take upper triangular that A when I is smaller than J, then it will be 0.
Yeah.
If other than A, I is smaller than J, other than value is 0, then it is also triangular matrix.
Can you ask your question again?
Means if you take upper triangular matrix,
Hmm?
then I greater than 0 will be 0. I greater
Yeah.
than J will be 0.
Yeah.
Suppose if I is smaller than J and it's 0, then it will be taken triangular or not.
Okay, I understand. So you are asking, for example, if you have a matrix like this, let's say 1, minus 2, 3, and 0, minus 1, 0, and here also 0, 0, let's say. So now is this a triangular matrix or not? You are asking, is that
Yes,
correct?
yes, ma'am.
So now this is of course you see the only condition we have to see is that whether the part below or above the diagonal are all 0 or not. Here this condition, if it is satisfied, you don't have to worry about the other entries. This is definitely a lower triangular matrix. Sorry, upper triangular matrix. Okay, you don't have to worry about the other entries. If this is 0, then it is triangular.
Yes.
Is that fine?
Yes, ma'am.
Okay, fine. Okay, so now let's move on to the topic determinants. Okay, so if you take any matrix A, particularly square matrix, here we are considering only square matrix. So then we can associate a number with this matrix, which is called the determinant, and it is denoted by determinant of A, or you can use this symbol. So please don't get confused this symbol with the modulus symbol. This is not modulus, this is determinant. When you have a matrix and you put like this, it is determinant. Don't confuse it with the modulus symbol. Okay. So now if you have a very small matrix, that is a 1 by 1 matrix with only one entry, then the determinant is just the number which you have here. So for example, if you are calling this as a matrix, so what is the determinant of A here?
-1.
Minus 1. Okay. So now if A is a 2 by 2 matrix like this, then you know the determinant is nothing but AD minus B. So for example, if you have a matrix like this, can you say what is the determinant of A?
7 minus
7
15.
minus 21. 7 minus.
Yeah.
-8.
So this is the determinant of a 2 by 2 matrix. So for 3 by 3, what are we going to do? So for 3 by 3, we have to consider all the 2 by 2 submatrices of this form and find the determinants and use this formula. You know, first we have to take this entry and consider the determinant of this part. Okay, and then minus A12 and consider the determinant of this part. We are leaving out the first row and the second column. A12 means you are having the first row and second column entry. So we are leaving the first row and second column. And the remaining entries are A21, A31, A23, A33. And then plus A13 and determinant of this part. Remember that when you are taking the second entry, there is a negative sign, whereas for the first and the last one, you have only a positive sign. Right? So this determinant, you already know what is the formula. If you apply, this is the formula for determinant of a 3 by 3 matrix. Alright. Okay, so very simple matrix if I give you. So for example, I give you a very simple matrix like this. Can you say what is the determinant of this matrix?
1.
1
Yeah.
into
If you are
minus
using
1.
some property, then you can
One.
yeah.
It would be
Yeah.
one.
So
1.
if you are using some
Then
property,
minus 1
Yeah,
into
it's lower triangular matrix, so we will multiply the diagonal.
minus 1 into 1.
yeah. So if you are using that it is a triangular matrix, then straight away you can tell. Otherwise, you can use the formula as usual and see that it is still 1. Okay, fine. Okay, so what is the determinant of an identity matrix?
1, ma'am.
1.
Yeah. So whether it is a 2 by 2 matrix, or let's use the proper notation. What is the notation of an identity matrix?
I, capital I.
Capital I.
Capital I. And if you want to specify the size of the matrix, then you can use the suffix like this 2. So I2 represents an identity matrix of size 2. And I3 means it represents 1 0 0 0 1 0 0 0 1. Okay. And what is the determinant of this identity matrix?
1.
1.
Yeah. So determinant of IN is 1 for any n in n. For any n in n. What is this n, you know, right?
Yes, natural number.
Natural numbers.
Yes.
They are the natural numbers. Okay, fine. So let us say you are having...
Excuse me, ma'am.
Yeah?
Ma'am, can you repeat the previous method that you were explaining about the multiplication of diagonals? Like, I was not able to understand.
So you are asking the property of a triangular matrix.
Yeah, right now.
So that we will explicitly do it later. Here I just wanted to use this formula and do it. When we are looking at the properties, we will see how the determinant of a triangular matrix is the product of diagonal entries. Okay. Right?
Okay.
We'll just see it soon. So here, determinant of A transpose means, what is A transpose? You know, let's say A is equal to A, B, C, D. What is determinant of A?
AD minus BC.
AD minus BC. Now, what is A transpose?
ACBD.
AC, BD. Now, what is the determinant of A transpose?
Same.
AD minus
BC.
BC.
So, AD minus BC. Again, it is same. So, what is that we know? Determinant of A is same as
Determinant of
Determinant of
Of
A
A
transpose.
transpose.
transpose. Okay. And determinant of product of matrices. Okay. Let us take very simple case of 2 by 2 matrices. Let's say 1, 2, 3 and 0. And then we have another matrix minus 1, 1, 1, 1. Okay. So now can you find what is the determinant of A?
minus 6.
Minus
Minus 6. And what is determinant of B?
Minus 2.
minus 2.
It is minus 2.
2.
Right? Now what is
Determinant of A is minus 5.
12.
See, 1 into 0 is 0 and then 3 2s are 6. Minus 6 is the determinant, right? 1 into 0 is 0, right?
Yeah, yes. Sorry.
Okay, fine.
AD
And
is 12.
yeah, so first let
Yes.
compute the product of this matrix. What is AB? Can you compute?
Yes.
1.
So minus 1, 2
Plus
into 1,
Plus
2, 1.
1,
and
3,
what is this entry?
1, 2,
3.
3.
3.
Yeah. And what is
B
this entry?
minus 3
Minus
Minus
3.
3.
Minus 3
and
and
0.
3.
3. Sorry, 3.
3.
Yes.
Now can you tell what is determinant of AB?
3 plus 9,
Minus
12.
Plus 9, 12.
3
Plus 9
plus 9, which
is
is
12.
12.
12.
Okay, both
Now
are same.
this is same as determinant of A into determinant of B.
B.
Correct?
Yes.
Minus 6
Okay.
into minus 12. Sorry, minus 2, which is 12. Correct? So in general, for any two matrices which are compatible with multiplication, you have determinant of AB equal to determinant of A into determinant of B. Alright. So this is the property when you have product of matrices. Okay. So what is the inverse of a matrix? How do we define it? Any matrix which satisfies this condition is called the inverse of a matrix. Right? This is the inverse of A. The procedure to find the inverse and all we will see it next week. So this A inverse equal to A inverse A equal to identity. This defines what is the inverse of a matrix. Any matrix satisfying this condition is called the inverse of a matrix. Now let us write the determinant of each of this part. Determinant of A inverse is same as determinant of A inverse A equal to determinant of I. Okay, first let us look at this part alone. So determinant of A into A inverse, how can we split this?
Determinant of A
Determinant
times
of
determinant of A inverse.
And what is the determinant of I?
1.
1. So what is the determinant of A inverse? If you know already what is determinant of A?
1 by determinant of A.
1 by determinant of A. In other words, you can also call it determinant of A, the whole inverse. Okay. So the same you can verify if you are considering this and this. Okay, the same you will get if you are considering just this two part alone. Okay, shall we verify it for maybe the same matrix which you have considered here? Let's take okay, maybe inverse we have not yet taught, so maybe I'll not go to the inverse of a matrix. Okay, so here we have a few matrices. So using the properties we have seen above, can you tell how to find the determinant of A power n?
So this will be determinant of A multiplied to itself n times.
n times.
Yeah,
N
so
time determinants of A.
yeah,
A
so
into determinant of A n minus 1.
Determinant of
see
A into
here determinant of product of matrices, it's not just for two matrices. We can actually write determinant of product of matrices. You don't have to worry about the number of matrices. Any finite number of matrices you take, determinant of product of matrices is same as product of their determinants. Okay,
So it
so
can be
for example,
determinant of A power n.
N multiplied by determinant of A, right?
yeah, so for example, if you have A squared, let us consider the simple case. A squared you can write as A into A. Yeah, so what is determinant of A squared?
determinant of A into
Determinant of A times
Determinant
determinant of A.
Yeah, so it means it is equal to determinant of A
Whole square.
whole square.
To the whole
Correct?
square.
Yeah. So the same if you have A cube, you can write it as now A squared into A. So you already know what is determinant of A squared now. So what is determinant of A cube then?
Determinant of A.
Determinant of A
A
square.
squared into determinant of A. So it means it is determinant of A
Whole cube.
whole cube. So in general, then what is determinant of A power n?
determinant of A
Determinant
whole
of
power n.
Determinant of A the whole power n. Is this clear?
S, ma'am. Yes,
Okay.
ma'am.
Okay, fine. So the next part here you have is A transpose A. So can you guess which property you have to use here? You have to use one or more properties maybe.
It will be
Yeah.
one.
One.
Product and
Two times determinant of A.
Yeah. So first of all, determinant of A transpose into A is equal to
Determinant
Determinant of A square.
Determinant of A trans.
A transpose into determinant of
A.
A. Now, what is determinant of A transpose into determinant of A is how can we write determinant of A transpose in terms of this?
determinant of A.
Determinant of A.
Determinant of A whole square.
Yeah. So it is determinant of A the whole
The whole
square.
square. Right.
Okay. So then obviously what can you say about determinant of A transpose?
It's the same thing.
Yeah.
Same thing, ma'am.
So it is again determinant of A the whole square. Right? Okay. Okay. What about P inverse AP? How can you find the determinant of this?
P inverse and P cancel.
How
P
can
inverse
you
of P equal
cancel
to
it
I.
straight away?
Identity matrix.
No, in between there is another matrix.
Date of A will be answer.
We can.
Ma'am, P will be
Which property we have to use here? Can anyone say it correctly? Which
Inverse.
property we have to
P
use?
inverse into
Date of
P
inverse.
We can multiply P on both
determinant is
sides.
I.
So determinant of P inverse AP. So you see a product of matrices.
Yeah,
So which property we have to use first?
Determinant of P
ma'am.
inverse.
Determinant of
Yeah, determinant of P inverse and then
Determinant
determinant of P.
determinant of A and then
Determinant of P.
Determinant of P.
now you have the determinant of inverse of a matrix. Now which property you will use?
1 by determinant of P.
Yeah, so you have 1 by determinant of P, determinant of A into
Determinant of P.
determinant of P. Is that all right?
Yeah, ma'am.
Yes, ma'am.
Okay, now you can here note that this property you will study soon. Here one thing you note that whenever you are writing 1 by some number, that number should be That number should be 1 by number
Greater
is
than zero.
valid
Not
if
zero.
Not
Not
zero.
Greater
zero.
than
the
zero.
matrix is non-zero. So you will soon see that if a matrix inverse exists, then the determinant is non-zero. This property you will study soon. So for now, we will assume this property. If A inverse exists, then the determinant is non-zero. We'll assume this so that you know that this is valid, that the denominator is non-zero. And now since it is a non-zero number, you can strike it out and then, yeah. Is anyone asking any question? If not, please mute yourself. Okay, so you see that determinant of P inverse AP is nothing but determinant of A. But please note that you cannot straight away cancel out, say that P inverse P is identity. You have to go through the steps and then finally say that it is determinant of A. You understand? Yes?
Yes, ma'am.
Yes,
Yes,
ma'am.
Yes,
ma'am.
Yes.
ma'am.
Okay, fine.
So
So from
excuse me,
the
ma'am.
beginning, yeah?
But it's still, I mean, if we cancel them, let's say P times P inverse becomes I, then still it will be the same answer.
But it is not the same process
No, but
because
we
we
can't.
cannot
No, but
directly multiply P
AB is
inverse
not
into
equal
P
to B.
because
No.
there is A in between.
Yes, there is a, but we can, I mean, first compute the matrices, multiply them, and then find the determinant at last.
No, no, this is not how it works. Uh,
It won't work because A into B, determinant of A into B is not the same of determinant of B into A. That's why.
Commutative property is not working,
Okay, okay, okay. Yes, yes,
right?
yes.
So we cannot say P inverse A into P is equal to P inverse into P into A.
Sorry, there was some issue with my internet connection. Just a minute. Yeah. So is the screen visible?
Not
No,
at.
ma'am.
No, ma'am.
No, ma'am.
Not visible,
Yes,
eh?
ma'am. Yes, ma'am.
Yeah,
Now it's
now
visible.
this is
Yeah,
Now
it's
it.
visible,
Now
ma'am.
it is visible, ma'am.
Okay.
Now it's visible.
Yeah. So you know that in general for any two matrix it's not commutative. Commutative in the sense you cannot shift AB and BA. If you can shift AB and BA, then in that case you can, what you can do is that put P here. You can shift this to and write it this way, and then P inverse P is identity times A and then A. But this is not the case always. You don't know whether AP is equal to PA. This you don't know. Okay, so you can
Yes, ma'am.
always shift it and write that P inverse AP is A. Okay, you understand what is the problem here?
Yes, ma'am. Got it now.
Yeah.
Yes, ma'am.
yeah,
Okay.
ma'am. I have one more doubt.
Yeah.
Uh, if we can do in determinant,
Hmm.
because determinant commutative property works in determinant, then we can shift determinant of P uh, one step below, and we can have determinant of P inverse into P into A.
Yeah, that way also we can do. Of course, that is another way of doing it. That is correct. So what is he saying is that we know that determinant property is commutative. Determinant of AB is equal to determinant of BA. This property is there. So he wants to use this property. Am I correct?
No, no, ma'am.
No? Okay. So
No.
what is that you are asking then?
Um, there is determinant of P inverse into determinant of A into determinant of P.
Yeah.
Yeah, we can have determinant of P earlier than determinant of A.
Yes.
Okay, and as as you mentioned a property
Mm.
where we can you can just write, then I can say better. What am I trying to say?
You want to say that you can write this determinant of P here and then determinant of A here.
Right.
And then what?
And then we can reverse the property, like you determinant of P inverse into A into P, you converted into the large form.
Okay.
Then we can also convert the large form into short form.
No. So you are saying that if no. What you are saying is not correct. Let's say you have determinant of let's say A, B, C. You are having three matrices here. Okay.
Right.
So let us say the orders are different, or even if the orders are same also, what you are saying is the determinant of A, B, C. You want to write determinant of A, determinant of B, and determinant of C. You simply want to exchange these two and
Right.
say determinant of A, determinant of C, determinant of B, and now
Right.
you want to write this as determinant of AC. Is this what you are saying?
ACB. Right.
No. You cannot write this in this way. You never know whether A and C multiplication is first of all possible, and you cannot write it this way. These are just numbers.
Okay.
Okay. So these are just numbers. So just shifting the numbers and then going back, this is wrong. No. So this is actually the straightforward method. You don't have to worry about all this. This is a very straightforward method. So don't worry about all this. So here you see that straight away you can use these properties and get this determinant of P inverse AP is determinant of A. Okay.
Okay. Okay.
Fine. In fact, there is this property, this name for this type of matrices. Suppose, let's say that this matrix is called B. Then, in that case, you call this matrix A and B are similar matrices. Okay. So, whenever the same matrix inverse and the matrix itself is multiplied in the front and back, then those matrices A and B, they are called similar matrices. Okay. This is just a comment here. This is not required. Just an information. Okay, fine. So,
Lavanya, 1 second.
yeah.
So that determinant of ABC thing,
Mm.
what you wrote down was right? Like determinant of ABC is determinant of AC into determinant of B. That is fine, right?
Determinant of
ABC.
mm,
You ultimately wrote it as determinant of AC into determinant of B, right? This
you
is
want to
right.
write it
No.
this,
Yeah.
but you never know whether AC this multiplication is always possible or not.
No. See. First of all, determinant of A, determinant of B, and determinant of C should exist, right?
Yeah.
So they are all square matrices.
Yeah.
And
Okay.
if
In that
ABC
case,
is happening,
in
yeah.
that case, the
Then,
order is the same. Yeah.
Yeah.
Okay.
They'll all
Fine.
be of the same order. Yeah. So irrespective of, it means we can write it like this, but I guess he was trying to ask if we can hence show that AB is equal to BA. That is not possible. In the sense that determinant of AB is equal to determinant of BA doesn't mean AB is equal to BA. I think that is what he was getting confused with. Whoever was asking the doubt, can you tell if that was your doubt?
Yeah, similar.
No, see, AB is equal to BA may or may not happen, but irrespective of whether they are equal or not, their determinants will always be equal. But you cannot go conversely. And this, what you said is right. Determinant of ABC is determinant of AC into determinant of B. That is right. But
This is
that
what
doesn't,
I was trying to
This
say.
is right, but from this you cannot tell anything about the matrices. You can only talk about their determinants.
Right. Right.
Someone muted me, it's showing.
Uri.
Okay, fine. So are you all able to hear me?
Yes, ma'am.
Yes, ma'am.
Yeah. So did you understand the point she is mentioning here? You can write it this way, but that does not mean that you can actually write P inverse AP as P inverse PA. Did you get that point?
Yes, ma'am.
Okay, fine.
Yes, ma'am. But
Okay.
determinant will always be A. Means determinant of A.
Yeah, this is correct. But from this property, you cannot just straight away shift the matrices like P inverse AP. You cannot write as P inverse PA. That is not possible. Okay, because we don't know the commutative property.
Excuse me, ma'am. Ma'am, for take 1 minute, ma'am. For taking out determinant of AC, if we will go with that, again the B will come in between, right? How can we do multiplication A into C?
Yeah, that is what here we are talking about. That is what I missed in the previous while I'm explaining in the previous place as well. So here we are just talking about the determinant and not the matrix multiplication here. We are just
taking out determinant of AC. We have to do that, right? Otherwise, we have to do like determinant of A into determinant of C.
Yeah, so the point I was thinking is that suppose let's say A, B, C all are different different sizes of matrices I was saying, but here determinant we know that it is defined only for square matrices, but so it is necessary that when we are talking about determinant of product of matrices, all the matrices must be of the same size n by n. Okay, so the product of AC is possible. Alright?
If they are of same size, all the three are of same
They
size,
will
then
be of the same size because we are talking about the determinant of a matrix. So the matrix must be a square matrix. Okay, all the matrices must be square matrices. So, and square matrices, when is a matrix multiplication possible? When all the rows and columns are equal. Number of rows and columns are equal. Okay. So in that case, you see that A and C both are of the same size, which is n by n, and so the matrix multiplication AC is possible.
Possible. Okay, yeah, got it.
Okay, fine.
So, ma'am, you cannot. A is 2 into 3 matrix. B is 3 into 2.
Okay.
And C is 2 into 2. Then it is multiplication possible, no?
But in that case, is determinant of A defined or determinant of B defined or determinant of C? Are they defined? You want each of the determinant to be defined, so each of them are square matrices, right?
Yes, ma'am. Sorry.
Okay.
Yeah, but even in this case,
Yeah.
square matrices can be of different sizes. So one can.
Yeah. Suppose, okay, fine. Suppose I come to what you're saying. Suppose let's say you are having a 2 by 2 matrix and I'm having another size matrix. The matrix multiplication itself is not possible here, right?
Exactly.
Yes.
Yeah. So in that case, all the matrices must be of the same size. All right.
Yes, ma'am.
Okay. Yeah. Okay, fine. Okay, so next let us look at.
It works only on square matrices.
Sorry.
It works only on square matrices.
Yes. Determinant works only for square matrices. Exactly.
Okay.
So P is not equal to P inverse, but determinant of P is equal to determinant of P inverse.
Sorry, can you say it again? Determinant of what?
P equal to determinant of P inverse.
No. Determinant of P is not equal to determinant of P inverse. What is the property of determinants? You know, determinant of P inverse is equal to what?
1 by determinant.
Yeah, 1 by determinant of P, not equal to determinant of P inverse. Okay, please don't confuse.
Okay, ma'am, we cannot multiply if the matrices are of course, we cannot multiply the square matrices if they are of different sizes, like 2 into 2, 3 into 3. But of course, we can multiply the determinants of them, right? Like we have 2 into 2.
See, in that case, you only can find what is determinant of A, B, C. Here, we are assuming that determinant of each of the matrices is defined. We are assuming that property here. In that case, yeah.
But if it is asked like determinant of ABC, we cannot multiply ABC, but we can multiply their determinants if they are of different sizes, square matrix.
No. ABC, this itself will not be defined if they are of different sizes. Then what is the meaning of determinant of that matrix? ABC itself will not be defined, right?
Okay, so if they are of different sizes, but they are of same matrix, still we cannot multiply their determinants. Correct?
What determinant of different sizes?
Yeah, let's say A is 2 cross 2, B is 3 cross 3, and C is 4 cross 4.
Definitely we cannot multiply, right?
Yeah, we cannot multiply. But I'm
Yeah.
asking if the question is asked, like, can we multiply the determinants of A, determinant of B? Then, of course, we can multiply, right?
Yeah, they are just numbers. Multiplying numbers is not a problem, but this property will not hold.
Okay, so that means the first one cannot happen, but the second one can happen. Like determinants of ABC is not possible, but determinant of A into determinant of B into determinant of C can happen.
Yes, they are just numbers you can multiply, but this property is not at all applicable in this case.
So we cannot do like this determinant of ABC if it is asked determinant of ABC in that case.
No,
we
no,
cannot
just
write it. We cannot split it like determinant of A into determinant of B and determinant of C, and then we multiply. We cannot do like that.
No. This ABC itself is not defined in that case. So this itself is not making any sense. You can only talk about these separate determinants, and you cannot talk about this at all in this case.
But there is a like property, right? Like determinant
That
of
is what
ABC.
that is what I'm saying. In this case, ABC itself is not defined, so the determinant is also not defined. So this does not make sense. Once this is not at all defined, then this does not make sense at all, right?
Okay.
It's only defined if they're all of same order.
Okay, you got my point?
Yes, ma'am.
Okay.
Thank you.
Okay, fine. So now let's look at determinant of triangular matrices. Already we have seen one example like this. So let's look at another example. Let's consider first the simple case 2 by 2 case, let's say. So now what is this matrix? Is this the upper or lower triangular matrix?
Upper triangular.
This is the upper triangular matrix. So what is the determinant of A if you are not using any properties but just calculating it using the formula? What is the answer?
Minus 3.
Minus 3.
Minus 1.
Minus 1. It's minus 3, right? Right? So now this is 1 into minus 3. That is the first diagonal into the second diagonal. Okay, so note this one. Let's look at another example. So let's say B is minus 3, 5, and 1. Now what is the determinant of B?
Minus 15.
Minus 15.
Minus 15. Right? Again, you note that it is nothing but minus 3 into 5. Now let us look at the 3 by 3 case. We have already seen one such example. So what is the determinant of this matrix?
2.
0.
2
Zero.
into 0.
It is 0. Suppose I am changing this 0 as 1, then
2.
That's
2.
yeah. So determinant of A is even if you calculate, what will you get? You will just get 2. That is 1 into 2 into 1. So what you can say in general for determinant of triangular matrix, it is same as
Product of diagonals.
Product of diagonal.
diagonal entries. Okay. Product of diagonal entries.
Is it same for both upper and lower triangular matrix?
Yeah, that is why I gave an upper triangular as well as a lower triangular matrix. You take any triangular matrix, this property holds that the determinant is equal to the product of the diagonal entries. Is that fine? Okay. So now let's consider determinant of matrix with 0 row or column. So let's say A is equal to 1, 3, 0, 0. So an entire row is now 0. So what is the determinant of this matrix?
Zero.
Zero, ma'am.
Okay. Same way,
Zero.
suppose let's consider a matrix where an entire column is 0. What will be the determinant?
0.
Zero.
0. So irrespective of the size, if you take any square matrix where one of the row or column is completely 0, then the determinant is always 0. Okay. So if a matrix has either a 0 row or a 0 column, then the determinant is 0. Alright? Okay. So I guess you know these row operations. Even if you don't know, don't worry. So we are going to consider these simple operations here. So what are these row operations? I will tell. So first operation here given is that we are switching two rows. If we are switching two rows, what happens to the determinant? That is what we are going to see. Okay.
It will go negative.
Yeah.
Sign change.
Yeah. So for example, let's start again with a simple matrix. Okay. So now what is the determinant of this matrix?
10.
Yeah. Is it correct?
10.
Yes.
10. Yes, ma'am.
10.
Yeah. So it is 10. Now what happens if so the symbol here is that I am interchanging R1 with R2. What is the matrix now? Can you tell? If I'm
Minus 10.
interchanging
4, 1
3,
minus 2.
3, 4, 1
3,
minus
4,
3, 4, 1 minus 2.
yeah. So in that case, what is your determinant?
Minus 10.
minus 10.
Minus 10. Right? So you see when two rows are interchanged, your determinant changes the sign. Let's now just shift the columns. Now what is the matrix?
Minus,
Minus
minus 2.
1, 3.
Minus 2, 1, 4, 3.
Yeah. So now what is the determinant of this matrix again?
Minus 10.
Minus 10.
Minus 10. So either you are interchanging two rows or two columns. What happens to the determinant? The determinant
Sign
changes
changes.
the sign. Yeah. So the sign of the determinant changes. Alright? Okay. So maybe a simple 3 by 3 case. You already know this case. So I'll use this one. What is the determinant of this matrix? You already know. What is the determinant of this?
1.
1. Now let's change R1 with R3, let's say. Okay. So if you are interchanging R1 with R3, what is the matrix you are getting?
0, 0, 1, 0, 1, 0, 1, 0, 0.
1, 0, 1, 0, 0.
Now what is the determinant of this matrix?
1 into minus 1.
Yeah, it is minus 1. Okay. So irrespective of the size, if you interchange any two rows or column, then you see that the determinant changes the sign. All right.
If we change one more time, ma'am, if we change one more row, then it will become again positive.
Yeah, so in that case, how you can see is that now you have this matrix. Now you want to interchange once again. It means now you are doing one more row operation. You are shifting two rows again. So again the sign change. So this minus again will change the sign into positive. Okay?
Yes.
Ma'am, for this we cannot multiply diagonal for getting determinant for this matrix.
No, this is not a diagonal matrix. No.
Okay.
Yeah. So this one usually is the diagonal matrix. This is called the principal diagonal. Okay, fine. So scalar multiplication of a row by a constant t multiplies the determinant by t. What does that mean? So let us say you are having a matrix like this. Okay. Now I am going to multiply just one row with some constant t. So let's say the constant is 2 now. So I'm going to multiply my R1 and replace with 2 times of R1. So what will happen to your A now?
2,
2,
6,
6, 2 minus
2,
2.
6, 2 minus 1.
Okay. Now let's call this matrix as A dash. So what is determinant of A?
minus 7.
Minus 2.
Minus 1
Minus
and
2.
yeah. And what is determinant of A dash?
Minus 14.
Minus
14.
Okay. So now you see what has happened. So when you are multiplying one row by a constant, then the determinant is multiplied by that constant. So here it is minus 7 into 2. So that is the determinant of A dash, correct? Okay. So now let us do the same for the column. Now let us replace the column 2, let us say, and multiply it minus 1, let me say. So I am replacing C2 with minus C2. So let me call that A double dash. What is the matrix you are getting when I am doing this row operation? Your first column remains the same. What happens to your second column when I do this operation here?
minus 3 plus 1.
Plus 1.
Now what is the determinant of A double dash?
7.
1,
7.
7.
7. Yeah, so it is minus 1 times minus 7. Okay, so what happened, what we are seeing is that when you multiply a row or a column, okay, when you multiply a row or a column by a constant, then the determinant gets multiplied by that constant. Okay.
Man,
Yeah.
if you multiply whole matrix by a constant, then
Yeah, we'll come to that now. Next, that is what we are going to see here. Okay. So, what is the determinant of this matrix?
Ma'am,
First of all, what? Yeah.
hello. Ma'am,
Yeah.
what have you written? Determinant of A transpose is minus 40.
No. This is just dash. I'm just using some different notation. A dash, A double dash, and it's not transpose. Transpose means I will write a T. This is not transpose. If it is confusing, maybe I will simply write it like B and C if it's confusing for you. Okay. B, C. So this is B and this is C. Okay. Yeah. So anytime if my handwriting or anything is not clear for you, please ask me immediately. Okay.
So,
Okay.
ma'am,
Yeah.
while changing the column that is minusing column 2 from column 2, what is the difference in determinant?
What happened? You see, determinant of the original matrix is minus 7, and when you change this, multiplied the second column with minus 1. What is the determinant you have you have got? You have got 7. So here your t is minus 1. So your determinant is multiplied with this t, which is minus 1.
Okay.
Okay.
Okay, thanks.
Okay. So now this is a diagonal matrix. Is that correct?
Yes, ma'am.
Yes.
Can I call a diagonal matrix triangular?
triangular.
Yes or no? Can I call it triangular?
Yes,
No?
ma'am. Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Is it upper or lower triangular?
Both.
It's only
Both.
triangular.
Yes. So a diagonal matrix is both upper triangular as well as lower triangular. We have already seen how to compute determinant of triangular matrix. So now can you say what is determinant of diagonal matrix?
Oh, diagonal. Yeah, 4 here. Diagonal entries multiplied.
So determinant of diagonal matrix is also, the property is same. What is the property? Determinant of diagonal matrix is equal to product of
Diagonal entries.
Okay. So now what is the determinant of this matrix?
4.
4. Okay. So now can you compare your identity matrix, 3 by 3 identity matrix with this matrix? Can you compare? Yeah. What is that we have done?
Multiplying 4 with upper row 1.
Row
Yeah.
1
So
we have
your
multiplied with
R1 we multiplied with 4. So what has happened? The determinant has become 4. Now what we are going to do is that I'm going to do this operation as well. So what does your matrix become now?
16.
Yeah, first of all, what is the matrix?
4 0 0
4 0 0. Then 0 4 0. 0 0 1.
Yeah. So now what is the determinant of this matrix?
16.
It is 16. Yeah. Now instead of doing this, so now I'm going to multiply, let's say R3 also again with 4 R3. Then you know, of course, what is the answer?
64.
64.
Yeah, you have 4, 4, 4 here, and all the other entries are 0. So what is that you see here? When you multiply a number for 2 rows, you get this, and you multiply for all the 3 rows, then it becomes
4 cube.
4 cube. Okay. So I guess you have seen a problem like this. So what is the
Yes.
observation we see from the previous case? If A is an n by n matrix, and if your B is alpha times A. Now this matrix is alpha times of I. What is your alpha here?
4.
4.
Yeah, 4 times of I. So your determinant of 4 times of I is nothing but 4 cube times of determinant of I. Is that correct?
Yes, ma'am.
Yeah.
Yes,
So
ma'am.
that is what is the observation we are seeing here. If A is an n by n matrix and B is equal to alpha times of A for any constant alpha, then your determinant of B is nothing but alpha power n times of determinant of A. Okay?
Yes,
Yes,
ma'am.
ma'am.
Yeah. So now you are considering A to be, see, this n is appearing here. Okay, so here we have a 3 by 3 matrix, and that's by 3. And now here again we are considering a 3 by 3 matrix. It is given that the determinant is non-zero. So you know determinant of A is non-zero. Okay. Now if determinant of 2 times of A is equal to k times of determinant of A, then what will be the value of k?
2 cube
8.
is 8.
2 cube.
Yeah, because from this property you know that determinant of 2 times of A is equal to 2 power, here what is your n?
And 3.
3.
3.
3 times
3.
of determinant of A.
A.
So it means your k is
2 cubes.
2 cube, which is 8. Is this clear for everyone?
Ma'am,
Yes,
Yeah?
ma'am.
I didn't
Yes,
get
ma'am.
it.
Yeah?
Madam,
Yeah?
I didn't get it, ma'am. Can you repeat it again? I
Yeah,
didn't got the question only.
yeah, sure, I'll tell you. See, you are having a 3 by 3 matrix and you know that the determinant is non-zero. Okay? And now they are saying that if 2 times of determinant of 2 times of A is equal to k times of determinant of A, this is given. Then what is the value of k they are asking. Now here we have to use the above observation. So what is the above observation? If B is equal to, here alpha A we are having 2A. Okay, let's call this matrix 2A as B. Then what is the property you know about the determinant of B? Determinant of B is 2 power n. So n is here 3 times determinant of A. Alright. And now what is that given here? Determinant of 2A is equal to k times of determinant of A. So here in place of k, what is the number you are having?
2 to the power 3.
Yeah. So that is why your k is 8. You understand?
Okay. Okay.
madam,
Yeah.
upper determinant of it's not scalar.
Yeah. 2 is just a scalar. It is just a number.
No, madam. Above example,
Yeah.
4 cube determinant. I that example.
Yeah.
That answer should not 4 because scalar multiple.
Yeah. The answer is here 4 cube, which is 64. What's your doubt?
If we multiply scalar value with determinant, then got 4. But here 4 cube.
Yeah. We
Then
got 4.
how we differentiate each multiply by scalar or its what's
Yeah. Please
I'm
ask.
trying to say that in place of
What is your question?
मैडम
multiplied by
जब हम स्केलर मल्टीप्लिकेशन करते हैं तो आंसर 4 आता है पर जब हम ये कौन सा ये वेक्टर मल्टीप्लाई करते हैं तब 4 क्यूब आ रहा है तो अब कैसे पता चलेगा कि वो स्केलर वाला है या ये वाला है
See, here in both the places we are multiplying with scalar. There is no vector multiplication. Okay, only difference in this and this case is that here you are multiplying with the scalar with only one row, whereas here you are multiplying this 4, the scalar 4, with the entire matrix. You understand the difference? Here you are multiplying the scalar 4 with only one row, whereas here you are multiplying the 4 with the entire matrix. Okay, so when you are multiplying with the entire matrix, then what happens is that when you are multiplying a scalar with the entire matrix, then this is the property you are getting, that the determinant of this multiplied matrix is nothing but the scalar power n times of the determinant of the original matrix. Did I clear your doubt or not?
No, madam, I not asked that question. In upper example, you give. Please scroll up.
Okay. Which one?
Up. Here, where is?
Which example you are talking about?
No, sir. No, ma'am. Not in. Not this lecture. Next time I ask.
Okay, fine. Sorry, I don't know what is. Yeah.
Ma'am, can you please scroll up to the properties of determinant second statement stating scalar multiplication of a row by a constant? Yeah. So over there, a little more. Yeah. So this over there, A matrix is basically being multiplied by 2, correct?
Yeah. What? Not the matrix, just the column. First row. Sorry, first row is multiplied by 2. Yeah.
Oh, I see. Okay, thank you.
It's not the entire matrix multiplied by 2.
All right, thank you, ma'am.
Okay. Okay.
I think he has a doubt that how do we come to know that we have to multiply the scalar by a single row or by the entire matrix? I think
It will be always specified here. This means that if you are writing alpha times of A, that means that you are going to multiply alpha with all the entries of A. Okay, whereas if I'm saying that something like this, R1, just replace R1 with 2 times of R1 or C2 with minus 1 times of C2, then it means I'm going to just multiply the scalar with only either the row or the column. Okay, but if I'm writing the scalar in front of a matrix, it means I'm going to multiply the scalar with all the entries of the matrix A. Am I clear?
Yes, ma'am.
Okay.
Excuse me, ma'am. Is this applicable only for the diagonal matrix?
No. If you are confused with that, because the computation is easier, I use this. Maybe I'll use this example: 1, 3, 2, minus 1. Okay, we have already seen the determinant. 1, 3, 2, minus 1. What is the determinant we have computed for this? Yeah?
Minus 7.
Minus 7.
Minus 7. Let us compute what is 2 times of A. What is 2 times of A?
Minus 14.
Minus 14.
No. 2 times of
2 times of A. A into
2, 6.
2,
2, 6, 4, 4 minus 2.
Now, what is the determinant of 2 times of A? Compute this determinant.
2 will come out, right?
Minus
2
4
determinant A,
and,
so minus 14.
Straight away you can compute it.
Ma'am, 4 come out.
20.
Yeah?
20.
4 come out.
2 square will come out. Minus 28.
Minus 20.
Minus 28.
Minus 2 square into 7.
And 2 square into minus 7.
Minus 28, which is
Yeah.
nothing but 4 times of minus 7. That is 2 squared into minus 7.
Minus 7.
So you see 2 square times of determinant of A. You got it? It's not just for diagonal matrix, for any matrix.
Okay.
Okay,
ma'am. Thank you.
Fine. Okay. So the next property we see is that multiples of rows and columns can be added together without changing the determinant's value. What does that mean? Let's see. Let's take a very simple example. Maybe the same example we can use. 1, 3, 2, minus 1. We already know what is the determinant. Now what I'm going to do, I'm going to add multiple of a row to another row. Let's say I'm going to replace R1 with 2 times of R1 plus 2 times of R2. I'm going to add. Okay, multiple of the second row, I'm adding it to R1. Can you say what is the resulting matrix?
5,
5.
Hmm. And then
1, 1,
One.
it is 1 or
One.
yeah, 1. Yeah, it's 1 only. Yeah. And then
2,
Two minus
minus
one.
1.
2 and minus 1.
so what is the determinant of this matrix? Can you compute it?
-7.
Minus 7.
Minus 7.
Minus 7. And you already know that this determinant is also minus 7. Correct? So it means what? When you are doing such an
Yes.
operation that you are adding a multiple of one row to another row, the determinant remains the same. It does not change. Okay. So I'll do the same maybe for the column as well. Let's say you are replacing C2 with C2 times minus, let's say minus 3 times of C1. What is the matrix you are getting? Let's call it A2.
1, 0.
1. So the first column is going to remain the
0.
same. This is 0. And then
Minus 7.
5. 5.
yeah, minus 1, minus
Minus
6.
7. Minus 7, man.
Yeah, minus 1, minus 6, minus 6. Now what is the determinant of this matrix?
-7.
Again, minus
Minus
7.
7.
So you understand what is the point here? When you are doing such an operation, that is, you are replacing one of the row or column with the sum of that row and the multiple of another row, then the determinant is not going to change. Is that clear? Yeah?
Yes,
Okay.
ma'am.
So now look at this question. Let A is equal to 1, 2, 3, 4 and B is equal to 7, 10, 3, 4. Can you first of all see what is the relationship between these two matrices?
In the matrix,
Yeah, man, second, first row is
Both are second row same.
2 times the second row plus first row.
Yeah, so
R1 is R1
Ma'am,
in the
R1
right.
is equal to R1 plus 2R2.
so in this matrix, if you are doing what operation can you get this one?
R1 plus 2R2.
Right? R1 plus 2R2. Right? So you have, this is the relationship between these two matrices. When you do this row operation, then you obtain this matrix B. Alright. So what is the determinant of A and what is the determinant of D then?
Minus 2.
it will
Minus
be same.
2.
So they both are the same.
Minus
Which is
Ma'am, can you give a general proof for this property?
general proof. Maybe we will see it after completing all the problems if we have time. And I don't think the proof is that simple to see it in this course. Okay. So determinant of A equal to determinant of B, both are same. And you can compute it separately and also check that both the determinants are same. Okay. Fine. Okay. Now look at this one. What is the determinant of this matrix?
0.
0.
0.
Okay. The determinant is 0. Mute. Yeah. So what is the relationship between these two rows? Can you say, or columns?
Excuse me, ma'am.
R2 is equal to
second row is
R2.
multiple of 2.
Yeah.
R2 is equal to
R2 tends
2
to
R1.
R1 is R1 to R2.
R2 equal to 2 R.
R2 is equal to 2 R1.
You can or you can say C2 is
C2 is
2
2
times.
2
C1.
is C to C1.
Okay, fine. Now, if I am doing a row operation, so the determinant is 0. Okay. So now let us say I am doing a row operation like this. I am going to replace R2 with R2 minus 2 R1. Then what will you get? Suppose the matrix you are writing 1, 2, and the second row becomes
0, 0.
0, 0. And you know that such an operation will not change the determinant of the matrix, correct?
Yes, ma'am.
Yes,
Yes, ma'am.
So you know that the determinant of this matrix is same of the determinant of this matrix. So already we know that if one row is completely 0, then the determinant is 0. Right? So in general, what you can say is that if you have one row or column as a multiple of the other, then I'm just giving the explanation behind why this determinant is 0. So it is very easy to see. That's why we are giving the explanation here. So if you always see that if you can write any one row as a
both
multiple
row
of,
are same.
yeah, either same means in that case your k is 1. Okay. So if you can write like this, or for the column also you can write in this case also, you see that if you have such a situation in your matrix, then the determinant is always 0. You understand why it is 0? Because you can do a simple elementary row operation and see that one of the row or column becomes 0, and you know that for that case the determinant is 0. Right?
Yes, ma'am.
Okay. So if a matrix A contains a row which is a multiple of another row, then the determinant equals to 0. Okay. So this observation is clear, right? Okay. So I guess you all have seen this question. So now I have given the clue that this is the observation you have to use here. Can anyone guess how to do this, or maybe you have done it already?
Ma'am, we can
Yeah.
separate SA31 into another matrix. So
Yeah.
and
So
then
can you do some row transformation here? So let me write this. Suppose I want to replace my R2. This is my R2 with R2 minus T times of R1. Okay. So what is the matrix I will be getting? Can you tell?
A11, A1,
Hmm.
A13,
And then?
SA3 minus SA3
minus SA31,
minus
SA32,
SA3. So
minus SA33.
And this remains the same.
Yes.
Okay. So what do you know? If we are doing such an operation, the determinant of A is same as the determinant of?
A1.
Yeah. You know this property already. Yeah. So what is the relationship between R2 and R3? Can you tell?
Taking the common.
R2 is S times of minus S times of R2.
R2 is equal to?
Minus S times of R3.
If you take
Minus
A
Minus
and
S
R
by R
common, then
times
it
S
will
R.
by
be
S
R.
by R.
zero.
Minus S by R times of R3.
R by R.
Yes, ma'am.
Yeah. So it means what? You are writing one row as a multiple of the other. You are already given that all these numbers are non-zero. It is okay to divide this number. So R2 is minus S by R times R3. So by the previous property, what is the determinant of A1 then?
0.
Yeah. So it means the determinant of A is also?
0.
Yeah. Is this clear for everyone? Yes?
Yes, ma'am.
Yes, ma'am.
Ma'am, here you do like divided with minus multiply with minus S by R.
Yeah.
We can also do like taking the minus S common with from R2 and taking common with from R3 is R.
Okay.
Also the having two same row and
And
Ma'am,
two
you can
same
take
row.
A and R common, and then it will
Then
be
it is
two
a
rows
determinant
same,
of
then it
A
will
is
be
equal to
0
two
zero.
rows will
directly.
be same.
Yeah. Yeah. The same argument may be used differently. It's correct. Okay. So I hope you all understood this problem.
No, ma'am, I didn't get this, ma'am. Determinant, after
Yeah.
the second operation, why it becomes 0, ma'am?
Come again.
To this part, did you understand?
Yeah, first
Madam, I
part, okay,
think
ma'am. R2 is
R2.
equal to R2 minus TR1 is okay. After that, determinant
Okay.
of A is equal to determinant of A1 there.
Yeah. Up to this, if you have understood, okay, I will tell this. So now this part is so your R2 is minus SA31 minus SA32 minus SA3. So this is your R3 now. Okay.
Yes.
So now let us multiply minus S by R with this row. So that is RA31, RA32, RA33. What is that you are getting? R and R will get cancelled. and so you will just get minus S times of A31 minus S times of A32 and minus S times of A33. Is that correct?
Correct, ma'am.
And
Yes.
that is nothing but your R2.
R2 is also the same thing.
Yeah.
So R2 and R3 are same.
Not R2 and R3 are same. They are having this relationship. If you multiply the R3 with minus S by R, so here your K is minus S by R. So when you are multiplying this R3 with this constant K, you see that your R2 and R3 are same. Okay, your R2 and this multiple of R3 are same.
Yes, we have made two rows equal, so that's why the
When two
determinant.
rows are multiples of each other, then the determinant is 0. So they are multiples of each other.
Yes, ma'am. Even if they are exactly same two rows, also it is 0.
Exactly. So in that case, your constant is 1. Yeah.
Yes, ma'am. Thank you.
Okay. Shall we move? Okay. Okay. So I guess there is one problem where you have something like this, right? Does anyone remember about this one?
Yes, ma'am.
So
Yes, ma'am.
yeah. So how to find the determinant of a matrix of this form? Can anyone give an idea?
Madam,
Yeah, then we can replace row 1 by subtracting row 1 from row 2 or row 1 minus row 2. Then second row will be written as R2 minus R3.
Yeah.
That's why we can find out the determinant will be A minus B, B minus C and C minus A.
Yeah, exactly. So did everyone manage to solve this?
No, ma'am. Can you?
Madam, is your mic has got some problem because it's causing a lot of distortion when you speak or two people speak.
Now is my voice clear?
Yes, ma'am, clear.
Okay. Okay.
Ma'am, here we
Yeah.
can.
Ma'am, one doubt, ma'am. Like, can we just do a column operation? Let's say C3 is equal to C2 into C3, so you get similar column. Like let's say like.
You should not multiply columns. No, that is not allowed. You can multiply by a number, not by a vector. If you are considering C2 into C3, it means you are multiplying two columns. No.
Oh, okay. Yeah. Yes.
Okay. Okay, so here again we can simply do some let's call this matrix maybe A. Let's first try to do some row operations so that we can simplify this matrix. Okay, so now maybe for example I can replace my second.
Sir, for ma'am, for simple understanding, we have to just first take the transpose of the A. Then I have to.
Ma'am, your sound is not coming clearly.
It's not from ma'am. It's another guy.
When someone else is talking, I guess my voice becomes not very clear.
Yes,
Okay. Okay, fine. So now let's say you are having R2 and R2 may be going to R2 minus R1. And the same we can do R3 minus R1. So these row operations, how I am choosing, if you are asking, by practice you can guess which row operations will be suitable for a specific problem. There are several ways you can do this row operations. This is just one possibility I am taking. As you do solve several problems, you can get an idea of which row operations are suitable for a specific problem. Okay, so this is one way of doing this problem. So let's say you are replacing R2 with R2 minus R1 and R3 with R3 minus R1. Now, what is the matrix obtained after doing this transformations? Can you tell?
1A, BC, 0, B minus A.
B minus A.
C into
C A minus BC.
C into B minus A.
Yeah. And then?
0,
C minus A,
C minus A.
AB minus BC.
So if you want, you can do one row operation at a time and then do the another row operation after that. So since you are now familiar, I'm doing both at the same time. You know that determinant of A is same as determinant of A1, right? Yeah.
Actually, while we are doing these two row operations once at a time, what kind of things we have to keep in mind so that we don't make a mistake?
See, as long as you are doing only row operations, and let us say this row operation suppose involves R2, then it is advisable to do it separately. Since this row operation does not include R3, I can do it. And same with this row operation does not include R2, I can do it. Okay?
Okay, ma'am.
Okay, fine.
Can I
So,
please repeat once more, ma'am?
see, if it is confusing, better do the row operations one by one. I guess you, for all of you, I suggest that do the row operations one by one. Here, what I'm saying is that this row operation is independent of the other row operation, that is R3. R3 is not involved in this first operation, and R2 is not involved in your next operation. That is why I'm doing it simultaneously. Otherwise, I suggest you to do it separately.
Okay.
Okay, fine. So now you know this, yeah?
Can we do here the column operation?
Yes, you can do column or row. That's what I said. There are several ways of doing it. This is just one way I'm showing it here.
Ma'am, if the first operation is involved in second one, then what if R2 is changed, then which means change version we should consider, or the earlier version?
Yeah, that is why I said that if that is involved in that, then first do one operation, write your matrix, and then go to the next operation. In that case, you will have three matrices for which the determinants are the same. Just to avoid this confusion of which R2, whether this R2 or this R2 you should use here, I'm saying you better go for the separate row operations rather than doing it at a stretch. Okay?
Okay, ma'am.
Okay,
There is
fine.
no advantage, no, ma'am, of changing the rows. Anyhow, if even from the A, we can find the determinant. And from A1 also, it's the same determinant. But from directly from A, if we find the determinant, it is
Yeah, that of course you can do that. But in your problem, I guess this A, B, C numbers are very huge. Because, yeah, that is why we are doing it this way. But you can, of course, do it in the usual way as well. If you can use maybe the transpose and do that, maybe that is also fine. It's completely fine.
Yes, right.
Okay, fine. So here I can now see that the determinant of A1, you see your R2, your you can note that your R2, if I can take your B minus A commonly, then it is 0, 1, and here I can take minus C maybe. Okay, so if I'm taking B minus A commonly, then and here I see only minus C is remaining, and same R3, if I am taking C minus A commonly, then I see 0, 1, and minus B is there. Okay, so you are when we are having this kind of a row number multiplied to a row, then you can write it as B minus A times C minus A, and then this matrix 1 A B C, 0 1 minus C, 0 1 minus B. Okay, so now, and here determinant is there, of course. What is the determinant of this matrix? Now it is very easy to compute because you have lot of zeros, so we can easily get them.
C minus B.
We can, in fact, someone suggested in the first that we can take the transpose. That I am doing it now because it makes the calculations easier. Yeah. So what is that you are getting? B minus. What is the determinant of this matrix?
C minus B.
C minus B.
C minus B. Okay. Okay, fine. So you got what is the determinant of this matrix. Okay. So
Excuse me, ma'am.
yeah.
Hello.
Yeah.
Can you explain this step where you multiplied B minus A into 0, 1 minus C, R2 equal to B minus A? How did you
No,
get that step?
I'm just taking B minus A commonly from this row because again see, here just 0 is there and here B minus A is here and this term CA minus DC. I can take C commonly, and then I get A minus B, and this I can write as minus C times of B minus A. Correct? So I can take B minus A commonly from this row. Similarly, I can take C minus E commonly from this row.
Hello, ma'am. I used another method. I wanted to ask if that method is valid. So,
yeah.
So what I did is, I first multiplied the first row with A.
Okay.
Second row with B.
Okay.
And third row with C.
Okay.
And then divided the third column with ABC. So
divided.
Yeah. So then I get 1. I get A square and 1. So using that property, I can.
So when you are multiplying with numbers, you have to be careful that you are multiplying the determinant also with those numbers. That's all.
Yeah,
I don't know exactly what is that you have used, but when you are doing, let's say you are multiplying the first row with A, so R1 replacing with A times of R1, you have to make sure that your determinant is now multiplied with this A.
Ma'am,
yeah.
If I change C3 or C2, multiply with, suppose I change C3 to C3 into C2. Then in C3 there is ABC, ABC, ABC.
Please hold on. You are saying the column C2 and C3 we are multiplying. Again, I'm saying I already told this. You cannot multiply columns.
Oh, we cannot multiply the columns.
No, no, no. You can only multiply the column or row with a number, not by a vector. Please remember.
Okay.
Okay, fine. Okay, so I guess we can move to the.
Hello.
Yeah. Anyone having doubt here?
Yes, ma'am. We converted row 1 from R1 to A1.
Sorry, your voice is not clear at all.
Hello.
Yeah.
Yes, ma'am. If we are multiplying any row or column by suppose, then we have to divide the determinant by A, not multiply by A.
You are multiplying a row by a number, so the determinant gets multiplied by a number, multiplied by that number. That is what is the property we have seen, right? What is that you are asking now?
Ma'am, a student earlier shared with us another way to solve this question. He said he multiplied first row with A.
Okay.
And along with that, he had to. You mentioned to him that for him to do that, he had to also multiply the whole determinant with A. Ma'am, that is incorrect. We have to multiply the whole determinant with 1 by A, not A.
Then what happens to this property here? What happens to this property here? Scalar multiplication of a row by a constant t multiplies by the determinant t, not 1 by t, right?
Yes, ma'am.
Ma'am, that's why we have to divide, actually.
I guess you are doing some reverse method of solving it. Okay, as long as the logic is correct, it's fine. But I don't know exactly what you have done. Unless I see it, I may not be able to tell it. Have you put it in your discourse, or where have you seen this common solution? I don't know. Maybe I can check it if you want.
I was just trying to say that it's not basically he's basically putting A out of nowhere in row 1. He's multiplying row 1 by A out of nowhere. So to negate that, to balance that, we have to divide the whole determinant by A also.
Okay, fine. That's fine.
This device.
Please don't get confused with what he is saying. I understand what he did.
Ma'am.
Connected the boat zone.
Hello. Hello. Am I audible, ma'am? Hello.
Yes. Can you hear me? Can you hear me?
Yeah, ma'am. He is just trying to.
Sorry, your voice is not audible. Someone is talking, but I don't hear anything. Sorry.
Hello. Now is this okay? Ma'am, he is trying to say that first we have to multiply A with the first row, B with the second row, and C with the third row.
Yeah.
But we have multiplied it, so we have to uh, keep the determinant same as the previous. So we have to divide A, B, C. Okay.
Yeah, that's correct only. Yeah. So to keep the determinant unchanged, he is doing that. That's fine. Okay. Okay. So let's look at determinants in terms of minus and cofactors. So in the previous method, so some students were doing it differently. Am I audible to everyone?
Yes, ma'am. Audible.
So there are several ways of doing a problem, as I already told you. So here, this problem, the previous problem, as the students are mentioning, so many different ways. As long as you are clear with one specific way, you stick to it. Don't get confused with all the techniques at a time. If you want to learn, of course you can learn, but don't get confused. Okay. So determinants in term of minus and cofactors. So here these are just some terms we are learning. It's not anything new. You have already seen how to calculate determinants. Now we are just giving some names for the notations we have used so far. That's all. So first I will start with what is a minor. So what is a minor of a matrix? We first consider any square matrix A. The minor of the entry in the ith row or jth row, also called the ijth minor, is the determinant of the submatrix formed by deleting the ith and jth column. Okay, so for example, you are considering this matrix A here. And if you want to consider, for example, maybe let's say M22. Okay, so what are the rows and columns you must be deleting from this matrix A?
Second row and second column.
Second
Yeah.
row and second column you must be deleting. So you must be calculating what is the determinant of this submatrix A11, A13, A31, A33. Fine. So this determinant you have to find. So same way for any Mij, you have to delete the ith row and jth column and find the determinant of the submatrix obtained by deleting these rows and column. Okay, so this is just what is called the minor. Is this clear? Calculating the minor? Okay.
Yes.
Okay. So from minor, you can calculate what is called as the cofactor. So what is cofactor? Cofactor is nothing but minus 1 power I plus j times Mij. Okay. So for example, if I am calculating maybe let's say C22, then it is nothing but minus 1 power, here I and j both are 2. So 2 plus 2 and then M22. And what is minus 1 power 2 plus 2?
1.
1.
Yeah. So it is simply M22. You can you can see that what is the this term, whether it is positive or negative 1, you can just see for a 3 by 3 case. For a 3 by 3 case, what will be the sign of this A11 for the cofactor?
Positive.
Positive.
So this is positive, this is
Negative.
Negative.
Positive.
positive,
Negative.
Negative.
Positive.
positive.
Negative.
Negative.
Positive.
Positive.
Negative.
Negative.
Positive.
Positive.
Okay, so this is what these signs are what here important when compared to this minor. Note that your minor is a number. Okay, please remember that your minor is a number. But cofactor, what is cofactor? So cofactor usually, yeah, here they are mentioning it as a number, but usually we write cofactor as a matrix together. Okay, so cofactor also is a number, but then what you do is that you write all the cofactors together as a cofactor matrix. So what is this cofactor matrix? So it has the entry C11, C12 and so on. Okay, CNN. So in this way you have this cofactor matrix, and this cofactor matrix is useful when calculating your A inverse. I guess many of you are familiar with the calculation of A inverse using this cofactor matrix. Okay, so
then what is adjoint, ma'am?
Yeah, adjoint is the transpose of this.
Okay.
Okay.
Thank you, ma'am.
Yeah. So let's first write down the determinant of A formula, which we already know. Yeah? Yeah, anyone is asking any doubt? Okay, fine. Yeah. If someone is asking a doubt, please ask clearly. Otherwise, please mute yourself. Okay. So let's write the determinant of A, which the formula which we already know. What is the formula which we already know? A11 times determinant of A22, A23. I don't know who is talking. Please mute yourself. Maybe I'll complete this and then you can ask your doubt. I don't know. It's interrupting my talk here. Okay. So A minus A12, A21, A23, A31, A33, and then plus A13, A21,
A22, A31, A32.
Okay. This is how we usually calculate the determinant. Am I correct? Now, can you tell this in terms of minors? So, what is this? What is this? What is this in terms of a minor?
M11.
M11.
This is M11. And this one?
M12.
M21.
And this one?
M13.
M13. All right. And again, the symbols, let's see. So, this one is a 1 here. Let's assume that there is a 1 here. So, this 1 is nothing but minus 1 per 1 plus 1. A11, M11, and minus is there. So here let's say minus 1 is there. So minus 1 per 1 plus 2 we can write this minus 1. I'm writing it this way. And here plus 1 is there. So that I'm writing as 1 plus 3. Sorry, A13 is missing. A13, M13. Now you see that what is fixed here through this term. Everywhere you see that this 1 is fixed. Okay, so this 1 is fixed. So this is AI. This 1 is your I. So J, M, 1, J. Okay, and minus 1 per 1 plus J. And now what is J? J is 1, 2, and 3. So you have summation J equal to 1 to 3. So now I have written this term in this way. Is that clear?
Yes,
ma'am.
Okay, so that is what is given here. So you see that determinant of A is summation J is equal to 1 to N minus 1 power I plus J, Aij, Mij. So the fixed I have considered here is that 1. So instead of this 1, you can write the same formula with 2 or 3. Okay, this is a 3 by 3 matrix. So 1, 2, 3 are the possibilities. Okay, so also you can vary your I by keeping your J fixed. That means you are calculating the determinant with the by starting with a column instead of a row. Okay, so when this formula comes in handy is that suppose let's say your 1 has a lot of big numbers and your 2 has maybe small numbers or many zeros are there in your second row. Then maybe you can use the determinant formula with I is equal to 2. That is when this formula comes in handy. Okay. So always, of course, row operation interchanging that technique is also there. But just know that this formula is used because suppose if you have any other row or column which are having smaller numbers or many zeros are there, in that case, this formula is useful to calculate the determinant. Okay, is that fine?
Yes, ma'am.
Okay. Okay. So I guess you have seen this problem already. Can you tell what is the answer for this?
1, 2, 3. Option A, B, C.
Option A, B, C. Is that correct? Can you explain it? So first one, I guess it is a straight away formula which you are using. 3 times the determinant of this part minus 2 times the determinant of this part and plus 2 times the determinant of this part. This is fine. Right. What about option B? Option B again here is
normal. And the second part is just column interchange so that minuses come out and minus is plus.
Yeah, so they are again using the first row only. But then what is that they have written? They have now interchanged these 2 columns. So when the columns are interchanged, the sign of the determinant changes, and so you see that the minus has become plus. Okay, so the same expression is written here. Only thing, the columns are interchanged, so the minus has become plus. Is that clear?
So,
Yes,
ma'am,
ma'am.
this option C will be equal to option D, no? Because it's changing its sign, positive and negative.
See, option C is not option A. See
The
here there
second
is
row. Option
which
C is regarding second row.
yeah. So option C they are using with respect to row 2. So they are starting with 2, 3, 2. So you see 2, 3, 2. We already have seen what are the signs for the cofactors. So here it will be minus, plus, minus. That is why here minus, plus, minus is there. And the remaining part minus 2 if you are taking, then this and this you have to leave out. So 2, 2, 1, 1. And then plus 3, determinant of 3, 2, 2, 1. And then minus 2, determinant of 3, 2, 2, 1. Okay, so this option is also correct. What happened to option D? What happened to option D? Why it is not correct? The signs in the cofactor matrix, they are not correct. Yeah? Yeah.
Minus 2.
Sorry, ma'am.
Option A and C are same, ma'am. Option A and C are same.
Option no. See, option A, they are doing the determinant with respect to row 1. Option C, they are finding the determinant with respect to R2 in the sense that you look at this formula here. So in the option A, they are considering this I as 1. In option C, they have considered that I as 2.
2.
Okay. And in option D also they are considering the I as 2, but they missed this point that you have to use minus 1 power I plus j we are using. That they missed. Alright?
Yes.
Okay.
So that is why the option D is incorrect. Is that fine?
Okay, ma'am.
Okay. Now let's move to the next problem. Suppose you are
Can
having
you
this
explain
matrix.
option 3 once again?
Option which one?
3, ma'am. Option 3.
So option C you are asking, right?
Yes,
okay.
ma'am.
Okay. So let us consider this matrix here. Now let's expand this in for the determinant of this. Let's expand this using your R2. So using your R2, what is the formula? First of all, let's write it. Determinant of A is equal to summation j is equal to 1 to 3 minus 1 power 2 plus j, because you are choosing your I is equal to 2, right? So minus 1 power 2 plus j, and then what? You are having your Cij's, right? Alpha ij. Yeah. So sorry, not alpha. Aij, mij. So what are your i's? Your i's are nothing but 2. So A2j, M2j. Right? So if you are having this, now let's expand it. So minus 1 power 2 plus 1. And what is A21? What is A21?
2.
Yeah, 2. Okay. And your M21 is, you are leaving out the second row and first column. So the determinant of 2 to 1, 1. Right? And then plus minus 1 power 2 plus 2 A22. What is your A22? A22 is 3.
3.
Your A22 is 3. So let's write 3 here. And then determinant of 3 to 2, 1. Alright. And then plus minus 1 power 2 plus 3. Your A23 is 2. And then determinant of 3 to 2, 1. Is that clear now?
Yeah, okay, ma'am. Thank you.
Okay, fine. Okay. So I guess maybe this is the last problem I have written. So I guess this is a very easy one only. Have you all solved this one?
Yes, ma'am.
Yeah, this is a very simple one. So you have to find the cofactor matrix here. That's all. And find the cofactor matrix which they are mentioning it as B, and find the determinant of B. So I guess no one had any difficulty doing this. Am I correct, or is anyone having any difficulty in this one as well?
Ma'am, if we apply the row operation or column operation, then also the after the cofactor is same or different? I guess it is different, huh?
Yes, exactly. Cofactor matrix will change when you are doing the row operations. So please don't do any such row operations when you are calculating the cofactor.
Okay, yeah.
Okay. Okay. So I guess then if you don't have any doubt in this case, then the gender.
No, ma'am.
Yeah.
This problem, just hint or how to solve this, ma'am.
See, this is very simple. So first let us maybe see what is Cij formula. First let's write. So what is the formula for Cij? Minus 1 power I plus j mij. Right? This is the formula for Cij. So what is your C11? C11 is minus 1 power 1 plus 1 mij. Sorry, M11. So it is simply M11. So you see that C12 is minus M12. C13 is same as M13. And C21 is minus M21. And C22 is M22. And C23 is minus M23. Am I correct?
Yes,
You're
ma'am.
following? Yeah. So C31 is M31 and C32 is minus M32 and C33 is M33. Okay. So now your job is only to find what is your minors. So if you know the minors, then you can do that. For example, what is M11? You have to just remove the first row and first column and calculate the determinant of the submatrix. This submatrix. Same way, what is the for example, let's say M12. So you have to remove the first row and second column and you consider the submatrix 4, 3, 3, 0 and calculate this determinant. And that gives you the minor M12. Same way M13 and so on. So M13 is 4 minus 1, 3 minus 2. Same way you calculate all the minors and you substitute it in this C11, C12. Depending on the signs, you just substitute and write the matrix C. So your matrix C is C11, C12, C13, C21, C22, C23, C31, C32, C33. So this is your matrix. So maybe this is your B here and you calculate the determinant of this matrix. That's all.
Ma'am, for calculating the cofactor, we should apply the ijth entry also, no? Means multiply the ijth entry also.
That is what I have done here. See,
You
so
have
you
not
may
multiplied.
no. That is for calculating the determinant, not the cofactor. Please don't get confused. So please see here, Cij is simply this formula. But when you are calculating the determinant, you are multiplying this matrix entries Aij, not in the cofactor itself. Okay. Okay. So,
What is difference between cofactor and minor? It is almost same, but the sign is changed only.
Exactly. Just the sign changes. That's all.
But rest all is same. Means
Yes.
minor and cofactor is. Okay. Minus and cofactor are same, but just the sign changes according to the position. Huh?
Yeah.
Okay.
Okay, fine. So I guess we have covered almost most of the topics from week 1. So far all the topics were clear today in this session.
Yes, ma'am. Yes,
Ma'am,
very
next slide, please.
Ma'am,
Next
there
slide.
was- There was a question, ma'am, in activity question.
In which one?
Ma'am, there is a type of form like ABC, BCA, CAB. There is any formula for determinant?
For which one?
Like a determinant ABC, BCA, and CAB.
Can you say what is the question number? Is it an activity question or what is that?
Activity question 1.4, question number 10.
Activity 1.4, question number 10. Just a minute. Okay, so here actually this problem straight away you can calculate the determinant from the ABC, BCA and CAP and just substitute the values of ABC. It's quite simple. I guess you don't even have to do any row operations. Straight away you calculate the determinant of A, B, C. I guess this is the problem you are asking. I'll just write it down. So you are asking, so A, B, C, B, C, A and C, A, B. If I'm correct, this is the question, right?
Yes, sir.
So if you want to calculate the determinant, so it is A minus CB minus A squared minus B times of B squared minus AC plus C times of BA minus C squared. So actually you will be getting minus A cube minus B cube minus C cube and then plus 3ABC. So in your question, what is your ABC? A is equal to 19, B is equal to 20, C is equal to 21.
Yeah, I am asking from this formula only. Okay.
Yeah, so 19, 20, 21. You simply substitute in this formula and calculate the answer. That's all.
Ma'am, I
Okay.
want to ask a doubt.
Yeah.
Suppose if we reduce any square matrix to upper triangular matrix using row transformation method, does
Okay.
does the determinant of the matrix will be same by the rule of product of the diagonal? Suppose there is a square matrix. Okay.
Yeah.
We reduce it by row operation to upper triangular matrix. Now, if we if we do the product of the entities of the diagonal, will it be equal to the determinant of the matrix?
So you are saying that you are converting a given matrix into a triangular matrix using
Upper
row
triangular.
operations.
Yes.
Okay, upper triangular. And you want to say you want to ask whether the determinant is the same.
Yes, if we do the product of the diagonal entries after reducing into upper triangular matrix.
Here the thing is that what are the row operations you are using, that we must keep in mind. I guess it should be same. Only thing here I'm finding out is that since here we have other operations as well, because see, in this case we know that the determinant is not changing, but for the other operations the determinant value is changing, right?
The determinant value is no. I mean, you said in line your last session that determinant doesn't change by using row operation.
Yeah, I am saying by row operation. I'm saying here which row operation you are asking. Which one I said?
I have taken for an example question number 7 of practice assignment. Okay, the matrix is 14, 14, 10, that's the first row, 0, 14, 4, that's the second row, minus 4, minus 18, minus 8, that's the third row. Then I have reduced it to...
just a minute, which problem you are talking?
Practice assignment question number 7.
Practice assignment.
Question number 7. You can use any other as well if you want to. I'm just giving an example. I have used this on this matrix, that's why I'm asking.
Okay.
So if I reduce it to upper triangular matrix, my answer was the first row is 14, 14, 10 by 14. Oh, sorry, my answer was 1, 1, 10 by 14. That was my first row. My second row was 0, 14, 4. And my third row is 0, 0, 8 by 7. Okay.
Okay.
But if we multiply the diagonal, 1 into 14 into 8 by 7, my answer would be 16, minus 16. Not, and this is not the original determinant.
See, the thing is that as I told you, the row operations, there are several different row operations. So all the three different things which I have discussed here. So you see that these are the three different row operations. Only the third row operation preserves the determinant. Only this one preserves the determinant. And in the other cases, the determinant changes. So it depends on what are the row operations you are using. So if you are using any of these two, then the determinant will change.
Okay, got it now. Thank you.
Yeah.
Thank you very much.
Yeah.
Excuse me, ma'am.
Yeah.
If this session is the thing is going new here, so may I leave?
If you don't have doubts, I guess we are done.
Okay, thank you, ma'am.
Hello, ma'am. Can I
have a
ask
doubt.
something? Can
Hello,
you
ma'am.
please share this PDF?
Yeah, sure. It will be shared.
Hello, ma'am. I have a doubt.
Yeah.
Ma'am, in graded assignment, in the last question, there is a link of discourse forum, and
Okay.
till now I have no access of this. So how I can do that question?
You don't have access to what?
Discourse forum. There is a link for discourse forum.
Okay, so I'm not familiar with this. Maybe you can.
I have sent. I have mailed several times to support team, but they are not. They are not solving my problem.
Okay.
Have you got the student mail ID?
Yeah, I have got a student email ID with password, and
Uh, and
I don't access
you
that
will
forum.
get the access. You will get the access. You write
I
to
am
support. You will
I
get the
am term
access.
student. I have a password with email ID, and how I can access that forum? I am using that password, but this is
So you
showing
must
that
be
you
able
are
to
using
use the
wrong
discourse.
credential.
You must be able to use the discourse if you are opening the link with your mail ID for this course.
Yes, ma'am. I am using. I am
You can
using
contact
that.
your house leader. They can provide you connect with discourse.
Can you
Ma'am,
give
in
me
our
their?
case, like it was something like somebody
Ma'am,
invited us and then only
Yeah.
we could
Yeah,
join.
yeah,
So
yeah.
maybe,
Someone invited us.
yeah, maybe
They,
you can ask one of your one of our seniors
Yeah,
to
your
send you
house
invite.
captain
Maybe
can
the
do that
TA
one.
or
Yeah. So
maybe.
as your
I
friends are
think
suggesting, maybe
ma'am,
someone. Yeah. Yeah.
ma'am, I have a doubt.
Yeah.
Ma'am, will there be any live session related to doubt? Like, will there be any doubt clearing session for a graded assignment?
See your graded assignment. Once your deadline is over, maybe you can ask during the your other session is there. I guess where TAs comes, you can ask the doubt. So solve with the sessions are there and open sessions also. Once the deadline is over, maybe you can discuss.
Okay, ma'am. Thank you, ma'am.
Okay. Okay. So maybe we can wind this up if you don't have any specific doubts related to the subject. Yeah.
Ma'am, I have a doubt.
Yeah.
In the graph question where there was two parallel lines.
Okay.
So, ma'am, as we have studied in the parallelogram theorem, we can drag the lines parallelly from one place to another. So, in this question, if we drag one line onto the other one, there will be many solutions. So, how can we say that parallel lines have no solutions?
So, what is your theorem? I don't know what is the theorem you are referring to, but what do you mean by dragging one line to the other? So, it means you are changing the equation, right? So, if a line is shifting its place, then the equation itself changes, right?
Yeah.
Yeah.
So, if the equation is changing, then of course, and the new equation intersects with the previous equation, then you have a solution. But the original equations, if they are parallel, definitely they will not have any solution.
Ma'am, maybe she is trying to ask according to from physics perspective. What happens is we can move one vector onto another vector, but we cannot change the direction of that vector and the length of that vector, by which we can derive parallelogram law of vector addition.
Okay, so if we are doing vector addition, then what happens? I still don't get the question maybe.
Ma'am, when we do vector addition in physics, we take one vector and put it on the tip of the another vector without changing the direction. We can move any vector, but we cannot change the direction of that vector.
So you are saying something. So let's say you are having two vectors. So you are saying that this is the sum. So instead of this vector, you are considering this vector. That is what you are asking?
Yes, ma'am. Yes. In physics, we do that. Tip, tail, and then we join the bottom to the top.
See here, they are just vectors and you are just calculating the sum. So the length and the other things are remaining the same. So that this does not matter. But whereas this is an equation, not just a vector. Okay, this is an equation, not any vector.
Equations are not equivalent to vectors.
No.
Okay,
So,
thank
for
you.
example, if I am taking y is equal to x, it represents the entire line itself. Whereas, if you are referring to a vector on this line, 1 comma 1 is a vector, 2 comma 2 is a vector. But this is an entire line. This is the equation y minus x is equal to 0. This is different from these vectors. Okay.
So we can say that a line is a combination of straight line vectors.
No, a line has infinitely many vectors on it. It's not combination of anything. Okay. So this is a line. So for example, this is your y is equal to x, means there are infinitely many vectors on this. Any vector of the form x comma x is lying on this line. Okay.
Okay, that means in physics, vectors is different from mathematics, right?
What do you say in physics? So in physics, do you say an equation as a vector? I don't understand now.
No, in physics, vector basically means anything which has a magnitude and a direction.
Of course, here also it is the same. Of course, here also it is the same, right? So if you take a vector, let's say the coordinates are x comma y. For this particular vector, you have a magnitude and a direction. But whereas y is equal to x is an infinite line, where the points on the line satisfies this property that y is equal to x. It is an infinite line. It is not a vector itself.
So we can say the line is a set of vectors.
Sorry, we call what?
We can say that in coordinate geometry, a straight line is a set of vectors satisfying that equation.
A straight line is a set of vectors. Okay.
Satisfying that equation.
And may I interrupt?
Yeah.
Hello, this is Astos here. Listen, vector has a different magnitude and a different direction, but lines don't have different magnitude. It's an infinite length of lines.
Yeah, it is an infinite line.
So you can't compare a line and a vector. Both are two different things.
For example, if you consider 1 comma 1, you know what is the direction. So you know this is the direction. But if you are considering y is equal to x, which is the direction you will say, this or this? This completely entire thing is this line completely is your equation. Here you don't know what is the direction, whether it is going up or down. It is just the entire line, and the magnitude here you cannot define at all. It is an infinite line. Okay.
Oh, okay, got it. Basically, we have a confusion because in physics we have a completely different definition of vector. That's why that confusion is coming.
Okay, fine. Okay, so any other doubts here?
Okay, ma'am. Just one last question. We had that CAJ calculation, right? The last question that we were discussing.
Yeah.
So I just want to understand if the B cofactor is correct. What are the numbers I have? I just want to get that corrected, because I mean I'm not getting the determinant A B as a correct answer. So
okay. I guess just a minute. I guess I have the answer.
Can you tell the determinant of? I mean, sorry, the B which I have calculated. Can you confirm if that is correct?
Yeah. Tell me.
Yeah. First row is 2, 3, minus 4.
Yeah.
Then second row is minus 6, minus 9, 5.
Yeah.
Third row is minus 1, 2, 2.
Yeah, everything is correct.
Okay. Then I don't know where I'm making wrong. So I'm getting final answer minus 23. So is that correct?
I guess the answer is 49.
Okay, then determinant calculation I'm making wrong. Okay.
Okay. So I guess then that's it. We'll see in the next session then.
Excuse me, ma'am.
Yeah.
I have a doubt in an activity question.
Okay.
Activity 1.5 question 10.
But I guess you are having the deadline till tonight, right?
No, ma'am. I have solved the other questions. It's just that question that I've left it.
But okay, fine. Let's see. I will not be able to tell the entire answer for it. Tell me which one.
Activity 1.5 question 10.
Oh, activity 1.5. It's non-graded one. Yeah. Tell me.
Question number 10. Suppose A and B are 3 into 3 matrices.
Yeah.
Such that the determinant of A is 4 and B is 3A.
Yeah.
Find the value of determinant A square B cube root.
Yeah.
So could you please explain the logic behind it?
See, it is a very simple question. You already know the property. What is the product of determinant of product of matrices you already know. So here you are first of all you have to see what is determinant of A squared B, and what is your A and B given as your
4 and 3A. B is 3A.
So your determinant of A is 4 and B is 3A. Determinant of A is 4 and B is given as 3 times of A. So here there are two properties which you have to consider. So you know if a matrix is of this form, then what is the determinant of B? We have seen a formula for this. Here A is given as a 3 by 3 matrix, correct?
Yes, ma'am.
So in that case, what is the formula we have seen today? Determinant of B is equal to 3 power 3 times of determinant of A, correct?
Yes, ma'am.
So if you don't remember, I'll show you the formula we have done here. We have used this. So see, determinant of B is alpha power n times of determinant of A. Okay, so this is the property we are using. So if we are using this property, then you know that this is 27 times of determinant of A, and you know what is determinant of A? It is 27 times of 4. Okay, and now you have to split this as determinant of A whole squared into determinant of B, and determinant of A whole square means 4 squared into determinant of B is 27 times of 4, right? So this is 4 cube into 3 cube actually, correct?
Yes, ma'am.
Is that correct? Yeah. So now what is the cube root of this? Cube root of 4 cube into 3 cube. So it's simply 4 into 3, right?
Yes, ma'am.
Okay.
Got it. Thank you, ma'am.
Okay. Okay. Fine. So.
Hello, ma'am.
Yeah.
Sorry.
Yeah.
Hello, Astos this side. So can we learn MATLAB parallel with the linear algebra?
Yeah, you can learn any programming language if you want.
Any
You can use MATLAB.
for learning MATLAB?
There are so many websites these days. I cannot specifically suggest anything. You can maybe there are some NPTEL courses also where they are teaching MATLAB, or you can use YouTube videos also. Sorry, I don't have any specific suggestions yet. Sorry.
Okay. Thank you.
Okay.
Ma'am,
Yeah.
one question.
Yeah.
Why they have given the deadline for practice assignment? Is it we have to submit before that? So
Of course, deadline. Yeah.
Earlier it was like from week 1 to 4 we have to submit before quiz 1 for bonus marks. So is it like that or what?
Sorry, I don't have any idea about this bonus marks and all. I'm quite new here. Better ask in discourse.
Okay, ma'am.
Okay.
Madam, how to approach question in practice assignment 1, 8, 9 and 10?
Practice assignment 8, 9 and 10. Just a minute. Okay, first of all, you have to write. So I guess it is some system of linear equations. So whatever given here, first of all, try to write that as equations. And once you have the equations with you, I guess you can write them as matrices and do it. The first 8th one, first try to write whatever is given in terms of equations. And the 9th one, if determinant, then how many medium size genes were? So what is your A here? Okay. I guess again here for this one, what is the relationship between your variables x, y, and z you are considering? So if you medium size, what you are representing, and what is the relationship between your determinant, you have to check, I guess. You have to write the equations explicitly to see what is the relationships. Is the matrix as above. What is the price of a t-shirt? Where price of a shirt is 2 and price of a jeans is 2. I guess all this you have to work it out by writing the equations from the given statement. First write everything as equations and then I guess you will be able to solve. Right? You will be getting 3 equations with 3 unknowns and 3 constants. So write them specifically, explicitly, then you will be able to understand the what is going on inside, I guess. Okay, please try it. Okay.
Okay, ma'am, there are three unknowns and the variables, the constant that was supposed to be, there is one unknown in those also. So the even if we are trying to find the x1, x2, x3, it is having like constant values in it.
That is why they have given determinant. So you have to see how you can use determinant there. Maybe if you find the determinant of the matrix, maybe you will be able to get some idea about the constants PQR. Okay.
Okay, okay, ma'am.
All right. Any other questions left?
Ma'am, one general question. So, suppose say we have a determinant of, say, here in this example, what you're showing, like it's b equal to 3a, right? So, I mean, something like that. If we have something like determinant of 3ab, I mean, in that formula. So I mean, if you have that the scalar multiplication 3 and then followed by a b, so should that be multiplied to both a and as well as b, or for only one of the matrix we should multiply?
So you are saying 3 times of AB. This is what you are asking, right? Determinant of what is the determinant of this?
Correct. If you have something like this, should I multiply 3 to
So
both?
first of all, you can split it like this.
Yeah.
And then you know how to write this.
Okay, so it's not that 3 should be multiplied to both a and b. So only for one.
Not necessarily. No.
Okay. Yeah. Thank you. Yeah, that clarifies.
Okay.
Ma'am.
Yeah.
Ma'am, how do we go about question number 7 and 8 of activity questions 1.3?
Okay, activity questions
1.3.
1.3.
Number 7 and 8.
Net 1.37 and 7 and 8, right?
Yes, ma'am.
So let x1 and x2 be solutions of the system ax equal to b. Which of the following options are correct? Is that what you are asking?
Yes, ma'am. Yes.
See, what do you mean by solution of a linear equation? So suppose you are given that ax is equal to b, and they are saying that x1 and x2 are solutions of this equations. It means what?
It means if we put
x1
x1 and
equal to
x2
b.
in x, then the equation will hold.
Yeah, so you can substitute x1 and x2 in place of x and the equation will satisfy. So you can write ax1 equal to b and ax2 equal to b. Now what is the question? The question they are asking is that is x1 plus x2 a solution of the system ax? So it means what? When you substitute x1 plus x2 in place of x, so will the equation still satisfy? So it means whether you will get b or not. So let's first split this. So you will get ax1 plus ax2, but you already know that this is equal to b and this is equal to b. So this is actually 2b. So this is not satisfying this equation, right? Same way. So what is the next option you are given? x1 plus x2, ax equal to 2b, of course. So just now we saw that this is actually satisfying the equation ax is equal to 2b, right?
Yes, ma'am.
Yeah. So and if you consider ax1 minus x2, then it is ax1 minus ax2. Then you know that it is b minus b, so it is 0. Okay.
Okay, ma'am. So basically, option second and fourth will be true.
Second and fourth, yeah.
Okay.
And I guess the same thing you have to do for
question number 8.
Yeah.
Okay, ma'am.
Only the
you.
system is different. Yeah. Fine. Okay, is that all? Okay then. So see you all in the next session.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank you. Bye.
Thank you, ma'am.
Thank you, ma'am.
Thank you.